Okay, let's take a look at part two here of the video, which we'll start with number 3. All right, so similar situation. Let's first draw in and here's what I mean by similar situation. It's an Atwood type machine, and we have to deal with different planes of motion and pretend that they're sort of one. We did a problem very similar to this in class. So we have this object having a normal force up in this direction and a force of gravity down in this direction. Normally we would point friction in this direction, but because there is zero coefficient of friction, then we don't have a resistive force. So this object is going to be pulled towards that pulley as a result of tension T. This object is going to be resisted from falling as a result of tension T, and then it's going to have a force down of F of Fg. Because both of these masses are 4 kilograms, I'm just going to call each of these mg. So this would also be mg, although it won't really matter so much for the one above it. All right. So I'm going to just cut here for a second to cut this video down for a second, and then I won't. I'm just going to go ahead and go through it. All right, so this is mass 2, as indicated right here. So here we go. Let's just move this in just a little bit. All right, so mass 2, so that's M2A. Right, so the sum of the forces on the first one is equal to just the tension. All right, and I'm calling this the positive direction and this the negative direction. Okay, and then I'll write next to it in this case, I'm going to write M1A, right, because that's the sum of the forces. Now it has 2 forces that are acting in this situation. It has that positive M1G, it's a weird G, and then it has a negative tension. Now in this particular case, both these masses are the same, so I could, and I guess I will. I'll drop these subscripts from each one of these terms so that I can see how they relate to one another, and then nicely cancel stuff out later on. So I already know what that tension is equal to. It's equal to just that MA, which means I can substitute that in. So copying this business down here and then getting rid of this tension here, and copying this term and moving it right down there. We've substituted in. So I can add this over to the other side, and this becomes 2MA is equal to mg. We have a m and an m in each one of these terms, which means that we're able to cancel those out, and so we get A is equal to g over 2. Okay, so that would be the acceleration of the system. So this is going to be a roughly 5 meters per second squared, or 4.9 if you want to deal with that. So we're good with that, and we didn't need the fact that those were 4 kilograms or not. But in the next question, we will need that. All right, so let me just pull up here real quick. The next question is question 4. And question 4 says, find the acceleration for this example, number 3, when mu is equal to 0.1. So now we are changing this scenario just a little bit to say that we now have friction. So these are mostly still the same. So I can bring these down here. Oops. For number 4, I guess I'll drop it in right there. The difference is going to be that we are now going to have this force of friction, as we talked about before, pointing back in this direction. So that changes this a little bit and makes it a little bit more complicated, but it doesn't really add to the difficulty. It just makes the question take longer. Okay, so now what we have here is for this first mass right here, this first object where we just had tension before, we're going to have to add in a term here of negative the force of friction. Now, kind of in a sidebar, I have to define what that force of friction is, right? I know that the force of friction is equal to mu times the normal force. And I know that because there's no other funny business going on, the normal force and the FG are just going to equal each other, because the normal force is what cancels out that y direction. And so that y direction here just has mg in it. So this now becomes mg. If these masses were different, I would need to call this M2G, but because these are of equal masses, I can just leave it like that, okay? So now I'm going to rewrite this. I'm going to say MA is equal to my tension minus mu mg. So a little bit more complicated in that sense. It's not going to be as nice and pretty for that acceleration as just a fraction there, because we have now added in these extra terms. But the same process still applies. I just need to solve one of these sides for tension and substitute into the other, and the whole systems of equations type thing. So I'll do that now. I'm going to move this term over to the other side, and that'll have a tension that's solved there, and then I can substitute it in over here. MA plus mu mg is equal to my tension. Okay, now we have these terms right here. Right, rewriting that down here, getting rid, I'm going to run out of space, huh? Getting rid of that, substituting this in, remembering that I need to throw that in here. Doing this again, but just distributing that negative sign through. Then we have this term right here. I'm going to need to move somewhere else in just a second. But I think I can do at least one more line here. Adding that MA over to the other side, we have 2MA is equal to minus, sorry, I got distracted. No, that's right. Well, no, I'll write it like this, is equal to mg minus mu mg. I'm going to pull out an mg from each one of those sides, or again, I can still notice that because I have a mass in each term here, here, and here, that I can then cancel it out from each one of those things. In doing so, I end up with the line that says, and I'm going to write that, am I? I'm going to write it right here, okay? 2A is equal to G minus mu G. Divide both sides by 2. And, you can do whatever algebra you want. Like, I could have this as G over 2 times 1 minus mu. And by pulling that out, that's maybe, if you're okay with that algebra, I can show you an intermediate step. Whoa, what's happening there? Show you an intermediate step if you want. So I divided both sides by 2. Well, let's do this. Let's do the intermediate step like this. This becomes G is 1 minus mu by pulling a G out of both one of those terms. And because I have the 2 right here, I can divide both sides by 2. But because I'm dividing everything by 2, it's like having a half. So we have that business going on there. Just sliding this up so I can continue my algebra. Right, and making an arrow, so later on you're like, what's happening? Then this, by substituting in some numbers, this is going to be equal to 10 over 2 times 1 minus whatever it is, 0.1. I think that's what it was, right? Yes, 0.1. So that is 5 times 0.9. Am I looking at that right? Yep, 5 times 0.9, so that's half. Wait, not half of it. That's just 10% is taken away, so 0.5 is taken away. So that means acceleration is 4.5 meters per second squared. All right, and so we have an answer right there. You can box that up all nice and neat. But we did it mostly algebraically. Okie dokie. So Now, number 5, which is conveniently right here, find mu for the acceleration being equal to 0. All right, so um, we need to see what that looks like. Okay. So what can we take away from up here? Well, we can really just reuse these lines and all the logic that goes along with it. When we wrote these lines, we were talking about the same situation, but now we're just changing it a bit. We're saying now I don't know what this mu is, whereas in number 4 we were saying the mu is zero point 0.1, and we're saying, hey, now the acceleration is 0. So how does that change any of these situations? Okay, so let's take a look and see if we can make sense of this. Let's just look at this left-hand term first. If this is 0, that means this whole side goes away. So what does that mean? Well, that means now that my force of friction is equal to my tension. Similarly, over here, all right, that means if this whole side goes away, that means that over here, my weight of that hanging object is equal to my tension. Okay. So now what do we see? Well, we know from before that mu mg is equal to the force of friction, and over here we see that mg still is equal to tension. I don't know why I rewrote that, but you're welcome. So now we can just substitute in what those things are equal to. So now by putting these two equations together, this now looks like mu mg is equal to mg. Interesting. And so we divide, because these have the same mass, right? It's still the same scenario. They're still both 4 kilograms, the same mass. It means that these don't carry along with them like a 2 or anything like that. So this situation is a special situation where mu is going to be equal to mg over mg. And as I said, if it was a different scenario, this would be like m1 and this would be m2 or something like that. Numerator and denominator respectively. So that means that mu is equal to 1 in this case. And so we're done with that question relatively quickly. And we can put a nice box around that, maybe. There we go. There we go. And no units there, nothing to worry about. Mu just would be equal to 1 in that case. And thinking about it more from a physicsy sort of way, I guess we would also have to say that the mu would have to be greater than 1. Is that what I want to say? It could be. It doesn't have to just be equal to 1, right? We know that it could be much greater than that. So any mu that was greater than 1 would be sufficient to stop this object from moving. It would mean, your force of static friction. Remember that when you're talking about static friction, you are talking about when the object isn't moving, you're talking about that inequality that goes on with that equation. Now, the other part of that is it says acceleration is equal to 0. It doesn't say not moving. So greater than or equal to 1 would be probably our best answer there. Moving on to number 6, the idea is explain in words and show with math what happens in number 3 as mass 2 becomes much smaller, right, in bold, much smaller than mass 1. Okay, what indeed will happen? And I'm gonna sort of leave this one to you for at least for now, but I'll draw your attention to at least one method that you can do. You can sort of imagine its initial acceleration, right, when they're equal. And so we had that answer up here somewhere. Here it is. It was g over 2. It was half. Okay, and that was really as a it was really as a proportion to what these masses are. Now, these masses were equal, so you could fall into the trap here, and this is kind of the trap that's been laid by me in this case, but the AP exam as well, to say that it doesn't matter, that mass doesn't matter. And the truth is that the mass does affect it, but it is more about the relationship, the ratio of mass 1 to mass 2. So you need to follow through with a setup similar to what we did in numbers 3, 4, and 5, but try to work out which one is bigger or which one is smaller, and we can talk about that more. Okay, and then numbers 7 and 8, I'm gonna leave for another time as well, and we can talk about those. But for now, I'll get this video up so that you can watch that.